Hi kids, this is your last notes video for the unit of sky and scale. We are going to be going over motions of the sky, diurnal and annual motion, precession of time, solar motions and sidereal and solar days, precession of the equinoxes and precession of Earth's axial tilt, and how to find coordinate systems on the celestial sphere. We can really break down all motion in the sky, whether it be the Earth, the Moon, or the Sun, into their rotation and their revolution. So rotation is what a body does on its axis. Revolution is the period of its orbit. So we can think about rotation as being like a day, and revolution as being a year. And everything in the solar system, with the exception of a moon of Neptune called Triton, rotates counterclockwise. That is the only body in the solar system that rotates clockwise, not counterclockwise. All of the rest of them move in that same direction. And in space, everything exists in nearly a flat plane. We have a galactic plane, we have a solar system plane. And within that plane, all of the planetary orbits are nearly circular. However, we will learn that they're actually not circles, they are ellipses, which result in changes of velocity as they approach the sun and as they are further away from the sun. So we can break down solar motions into diurnal motion, which means daily motion, and annual motion, which would be yearly or beyond yearly motion. So the diurnal motion is when we see the sun rise in the east and set in the west. And I want to point out what looks like a little formatting error here. This symbol is actually degrees. So we know that the sun moves across our sky about 15 degrees an hour. And we get that from taking 360 degrees divided by 24 hours. We get 15 degrees. It's not 150, which breaks down to about 1 degree every 4 minutes or so. So that is our diurnal motion as we perceive the sun moving across the sky. And if we were to look in this image here, we can see that the path of the sun changes throughout the year. So we can see during the summer, the sun is the highest in our sky. During the equinoxes around spring and fall, it's about middle of the sky or so. And during the winter, it is the lowest in our sky. So December 21st would be our winter solstice, which would be our shortest day when the sun has the lowest path across the sky. June 21st would be our summer solstice when the sun has the highest path across the sky. And this would be pretty darn relevant to what our latitude would be in the path of the sun, because we would not see the sun pass directly overhead, nor very low because we're at 34 degrees latitude. So one of the ways that we can measure annual motion has to do with the precession of time. And we think of a year as being 365 days going from January 1st to January 1st. But it's really the time that it takes for the Earth to get realigned with the background stars. And this concept is true for both a day, a year, and a month. It's not necessarily just the passage of time, it's the realignment. And as we'll see, the passage of time and the realignment are not necessarily the same thing. So we have differences between what a true day and month are and what we account them to be. So a sidereal year is actually the equinox to the equinox. And this precesses with a variation of about 20 minutes a year. This is one of the reasons that we have the necessity for a leap year. Little fun fact for you, our calendar is based on the Gregorian calendar, which was made by Pope Gregory in the 1500s, but prior to that we had the Julian calendar, which was created in 300 AD by Julius Caesar. So we had days that were dropped from the month of October in 1582 to realign with the dates for seasons, religious holidays, as that was switched from the Julian to the Gregorian calendar. But we've used this calendric system for 500 years, which is just a variation from the Julian calendar of 300 AD. And prior to that, the Julian calendar was to realign all of the cultures within Greater Rome to have the same calendric system, because we had the groups that were using a solar system, some that were using a lunar system, and there were groups that were years off from each other. So around 300 AD, the Julian calendar was created to unify all of the different calendric systems. So here I've got this little video that tells you some more little tidbits about leap years.
People have been keeping track of time pretty much since people were people. At first, we just needed to have an idea of what season it was, and maybe what season was coming up next and around when. But after the invention of agriculture, it started being important to keep track of each day of the year. Once you start trying to count the days of the year, though, it doesn't take long to notice a problem. You just can't make a consistent calendar with the same number of days every year because there aren't a whole number of days in the year. That is why today's date exists. We have to add an extra day to the calendar every now and then, and we do it on February 29th. The main issue here is that the Earth's orbit and its rotation don't have anything to do with each other. When our planet spins once around on its axis, we call that a day, and when it completes a full orbit of the sun, we call that a solar year. Now, it would be nice if Earth always got back to the same place in its orbit after a set number of complete rotations, which would be an exact number of days, but it doesn't. Earth orbits the sun once every 365.2425 rotations, so if your calendar has a whole number of days, like 365 or 366, then you're counting either too few days or too many. And if you're counting wrong, then things like the solstices, the longest and shortest days of the year, which always happen at the same point of the Earth's orbit, will move around the calendar. That makes it a little tricky to plan for events that you want to happen on the same day every year, say a solstice celebration. And as if that wasn't complicated enough, a lot of ancient cultures like the Babylonians, Chinese, and Romans used calendars based on the moon. But the behavior of the moon, again, has nothing to do with our rotation or our orbit. The moon goes through a little more than 12 cycles, each a little more than 29 days in the time that it takes for the Earth to go around the sun. And that means they had a similar problem. 12 lunar months a year is too few, but 13 lunar months in a year is too many. So most people using a lunar calendar would have 12 months most years, but then they'd add an extra month every couple of years to keep things like harvest around roughly the same solar date. Then there were the Romans. They're always trying to keep things interesting. Instead of having a system in place for how often there should be an extra month, they left it up to their highest religious authority, the Pontifex Maximus, which kind of worked for a while, at least until Julius Caesar came along. The Romans thought adding those extra months was super bad luck, so they didn't want to do it while they were at war, and Julius was at war all the time, so the calendar got way off from where it should have been. So eventually Caesar decided that the Romans should just use a brand new calendar that relied on a set system of when and where to add extra days. And that's how we got the Julian calendar, which Western Europe and Christian churches used for a really long time. Most Julian years had 365 days, but like we said earlier, the year is about a quarter of a day longer than that, so every fourth year got an extra 366th day. Seems like a good fix, but things are not that simple. The 4-year system ends up slightly overestimating the length of the year by about 10 minutes, something the designers of the Julian calendar knew about, but they decided it wasn't worth complicating the calendar over. It's 10 minutes a year. What could go wrong? Well, 10 minutes a year over a lot of years can really add up. By the late 1500s, around 1600 years after Caesar, the calendar was about 13 days off from where it should have been. That's when Pope Gregory XIII, the Pontifex Maximus of the Catholic Church at the time, decided that the Julian calendar needed an overhaul. So he put together the Gregorian calendar, the one that we still use today, which is really just the Julian calendar with a couple of changes. The Gregorian calendar's new rules were every 4 years, add an extra day. Except, don't add it when the year is divisible by 100, except actually do add it if the year is divisible by 400. So 1700, 1800, and 1900 weren't leap years because they were all divisible by 100, but not by 400. But the year 2000 was a leap year since 2000 is divisible by 400. And of course 2016 is a leap year as well. If we were still using the Julian calendar, 2016 would still be a leap year, but the calendar would now be behind by 16 days, so this video would have been uploaded on February 13th, 2016, not February 29th, so it wouldn't have made any sense. But the universe is complicated and does not care about our calendars, so the Gregorian calendar is still a little bit too long. We will add a day about every 7,700 years. But don't hold your breath for a new calendar. The Gregorian calendar was only introduced when the Julian one was 13 days off from the true date, and that won't happen to the Gregorian calendar for another 100,000 years or so. Thank you for watching this episode of SciShow, which was brought to you by our patrons on Patreon. If you want to help support the show, you can go to patreon.com/SciShow. We always very much appreciate that. It is the reason why we can do all this. And if you want to keep getting smarter with us, as always, go to youtube.com.
So hopefully that video played. The slide just kind of breaks down everything that video said. So we have leap years almost every 4 years. And honestly, guys, I would not test you on the nitty-gritty of leap years. I just think that it is interesting that, you know, our calendric system is based on this and how we have had to use this different system and how we've had to devise time based on the annual motions of the sun. The motions of the sky do not just determine what time of year it is, but also the sort of climate that we have in an area. So seasons are caused by our tilt and our changing position around the sun. So we can see that if each of these different rays of sun reflect a different angle of sunlight as it reaches Earth, we can call this the angle of insolation. We could see that our higher latitudes, our equator being 0, our poles being 90, 40 being somewhere around mid, we are located at 34. We could see our higher latitudes receive a lower angle of sunlight. The sunlight is more spread out, so those areas get less direct rays of sun. It is therefore going to be colder. This is why the poles are cold, the equator is hot. So we could see, just using this flashlight as a comparison, summer solstice, which would be when the sun is the highest in the sky, would be when we would get the most concentrated rays of sun. Winter solstice, the shortest day of the year, would be when we would get the most dispersed rays of sunlight. So on the winter solstice, when the sun is the lowest in the sky, we would get sun at a much lower angle, which would spread out and disperse the rays of sun, and would create a cooler climate because you have the same amount of sunlight spread over a far larger area. Therefore, it is less concentrated. And we call this the angle of incident sunlight, or angle of insolation, like insulation in your walls. So one of the questions that I would ask that you know would be to be able to recognize which latitudes receive the highest and the lowest angles of insolation. So remember that our equator is latitude 0, and our poles, let's make this red, our poles are going to be latitude 90. So our poles are 90, our equator is 0, we are at 34, and up here would be somewhere around 60. So we have our mid-latitudes, we have our low latitudes, we have our high latitudes, and I would expect you to recognize that your lower latitudes receive the most direct rays of sun, which is a higher angle of insolation. We could see that this angle here is the closest you can get to 90, whereas our 90 degrees latitude receives the lowest angles of sun. So don't be confused between angle of sunlight and latitude. So high latitude, low angle, low latitude, high angle. One major misconception is that our seasons are caused by our changing distance from the sun, but this is actually not true in the slightest. We are actually closer to the sun in January than we are in June, and our distance from the sun varies very, very little. Our orbit is nearly perfectly circular. So due to it being nearly perfectly circularized, there is no real place for it to be further from the sun or closer from the sun, as opposed to orbits such as Mars, which are a bit more elliptical, which would take it closer to the sun and further away. So the difference between Mars's winter and summer is about 45 days. It is more extreme, but our seasons are nearly perfectly even because our orbit is nearly perfectly circularized. So the reason that we have the seasons is because Earth's axis is tilted at 23.5 degrees, which is exactly what the Martian orbit is tilted. And that is because Earth, early on in its history, was hit by an asteroid. It may have been the moon-forming impact that knocked it on its side. So all of the planets in the solar system have different degrees of axial tilt. Venus is nearly perfectly upright, however, it rotates backwards. And Mars is inclined at the same degree. Uranus is inclined at 67 degrees, so it's almost entirely on its side. These are all as a result of early impacts. But this tilt is what gives us our seasons. So because we are tilted at 23.5 degrees, as we move around the sun, different hemispheres get either more or less incoming solar radiation than the other hemispheres. So during the summer would be when the northern hemisphere is tilted towards the sun. During the winter is when the northern hemisphere is tilted away. And this results in us having opposite seasons in each hemisphere. So during summer in the northern hemisphere, it would be winter then in the southern hemisphere. And it's not because the tilt changes, it's our orbital position around the sun. And that results in one hemisphere being pointed towards or away from the sun. So here we can see the breakdown of the different solstices and equinoxes. These are always generally within 1 or 2 days of each other, and this is because this is based on where the location of the sun is. So we think about the sun is rising in the east and setting in the west, but this only happens perfectly on the date of the equinoxes. And remember, that's what we measure our sidereal year from. So the altitude of the sun is what changes. And as we've already looked at, we can see that we have this varying, changing angle of sunlight. During the summer would be the highest in the sky, during the winter would be the lowest, and the closer you are to the equator, the higher that path of sun would be, and you would see less variation. The further north you are, the more variation you would have. This results in the poles having winters where the sun may barely crest above the horizon. One of my sisters lives in Fairbanks, Alaska, which is just below the Arctic Circle, 8 miles from the actual town of North Pole, where your letters to Santa actually go. And during the winter, it's like it's twilight all the time. The sun doesn't come up until about 3 in the afternoon. It's only up for about 3 hours, and the sun only makes the sky about a reddish pinkish glow. It never actually makes the sky blue. One of the things I've mentioned a couple times is sidereal motion, and I want to make sure you guys have an understanding of how this differs from synodic or solar motion. So sidereal motion, we could think about this as being the real motion. I like to tell students that this is like the 360-degree full motion of something, the process of returning to the same position with respect to the background stars. But it's important to recognize that realigning with the background stars may not put us back into realignment with the sun. So in terms of our daily motion, we have a sidereal motion where Earth does a full 360-degree rotation on its axis, which means we realign with the stars behind us. But we may not realign with the sun. The sun may not be the exact same place in our sky after we do a full rotation, and that's because, in addition to rotating, we are also revolving around the sun. So we have our motion in our orbit and on our axis. So our synodic motion, it's synodic when it's referencing a month, solar when it's referencing a day, relates to our motion which results in the same view of either the sun or the moon. This is what we base both our day and our month off of, is this guy right here. So the sidereal motion is the real motion. The synodic or the solar motion would be what we base our month or our day upon. And this is an actual real difference based on those rotations. So a sidereal day, you can see, is not quite a whole day. This is one of the reasons we have leap years at all. So a solar day, what we base our day off of, is 24 hours. So if we look at just our position 1, so this would be on day 1. So when we move from day 1 to day 2, after we've done a sidereal rotation, one sidereal day, it's done a full 360 motion, but we can see we're not realigned with the sun. So it takes an extra degree of rotation. So here we've done 360 degrees of rotation, but it takes 361 degrees of rotation to realign with the sun. So a solar day is actually longer than the time it takes us to just do a 360-degree rotation. So a sidereal day is shorter. That's just the time it takes to rotate. A solar day is the time to realign. And in terms of months, you don't need to know this now, but just as an example, we will go over this during our moon unit. Coincidentally, that is the name of Frank Zappa's son. Why would you do that? I don't know. But a synodic month, we can see the complete lunar cycle. A synodic month would be from new moon to new moon, and that would be from our time 0 here up to here. That is new moon to new moon, which is just over 29.5 days. A sidereal month is actually 2.5 days, nearly shorter, and that's just the time it takes for the moon to do one complete rotation around us. But you can see that when the moon does one complete rotation around us, it's not realigned with the sun. We do not get the same lunar phase. So in order for it to give us the same lunar phase, it has to rotate for an additional 2.3 days. Another type of annual motion we have is called precession. Precession is something that all rotating objects do, where the axis of rotation actually wobbles. So although we call this annual motion, this is actually much larger than annually. This is over a 26,000 year cycle. It would take us 26,000 years for us to realign back with Polaris as our North Star. So precession causes our axis to wobble, much like a top if you were to spin a top. So our precession is only a couple of degrees. But if a whole cycle is 26,000 years, half of that, 13,000 years, we would have a different North Star. So the exact opposite in the sky, in terms of our axial rotation from Polaris, is the star Vega. So in about 15,000 years or so, approximately, one of the brightest stars in our sky, Vega, would be our North Star. So our precession is not very large. It's only about 2 to 3 degrees. However, Mars has an axial precession of 45 degrees. So that planet, and that's largely due to the fact that it does not have a large stabilizing moon like we do. It has 2 very small captured asteroid moons, which do not stabilize its axis. So its axis swings very wildly. So that may be some of the reasons that we see evidence of past climates on Mars. The last thing that we are covering in this unit has to do with parallax and being able to determine how far away a star is based on its relative motion. So what an astronomer would do would be to look at where a star is from 2 different vantage points, and the star itself does not move. We, the observers, are the ones that are moving. And we would see, based on our motion, how that star appears to move in relation to the background stars. You can simulate this if you were to cover your left eye. If you look straight ahead of you right now, find an object that's straight ahead of you, at least a decent distance away, cover your left eye. Now cover your right eye, and see how those objects appear to change position. So that same object, right now I'm staring at a door, and if I cover my left eye and then my right eye, the position moves. That's parallax. That's exactly what that is. So we can do this in terms of the sky, because obviously these distances are far greater than something 10 meters away from you, by taking the largest vantage point that any observer on Earth could ever be away from themselves, which would be opposite sides of the orbit. So this wouldn't just be one side of Earth and then the other. Remember, our closest star is 4.5 light years away. So we're looking at things that are all very, very distant. So taking Earth's position in, say, January, Earth's position in June, looking at them 6 months apart and seeing the same star where it appears in the sky in each of those orbital positions. So all of these angles are going to be very small. We could measure this angle right here. That's our parallax angle. So we'd look at those angles 6 months apart, and we could determine with very simple division how far away approximately that star is. But the more distant stars are going to have, as you can imagine, a much smaller angle. So the limit here is about 50 parsecs. So this would only be really stars in our stellar neighborhood, not elsewhere in the galaxy, and definitely not outside of our galaxy. So here's another image showing our orbital position. So here would be in January, here would be in July. So the maximum distance we could be apart would be 2 AUs, because we have 1 AU on either side. So here is our star, here is the angle as it would appear against the background stars. So here would be that star in January. Here we could see that star 6 months later in July, which actually would be 7 months later, and we could measure those angles to get a distance. So here we can see that again. And the formula is very simple. It is just that your distance is equivalent to 1 divided by your parallax angle. And that would give us a distance in parsecs, which we could then convert over to light years. So for example, Sirius is relatively close by, and this has a parallax angle of approximately 0.379 arc seconds. So here we can see approximately how much portion of sky each degree would comprise. And you will need this for your observations to be able to measure the motions of the moon and the sun across the sky. So you can think about your pinky as comprising 1 degree, your 3 fingers 5 degrees, and so forth. The biggest measurement you could do with your hand would be 25 degrees. Remember, there's 360 degrees in a circle. And we could further break down this 1 degree into minutes. So within each 1 degree, there are 60 minutes, right? And in 60 minutes, we could further break that down into 60 seconds. And 60 seconds we could break down further into 60 arc seconds. So every degree would have 3,600 3,600 seconds. So to go back to our previous slide of Vega having 0.3 arc seconds, I mean, realize these are very, very small distances. So this would be a fraction of this measurement right here, of your pinky in the sky. So early astronomers, one of the reasons that they ruled out that the Earth was rotating around another body is they did not calculate, they did not determine or measure parallax. And you can see that, you know, Vega has one of the largest parallax angles, which is 0.3, and that's arc seconds, not minutes of arc. So much smaller than your pinky. We know that this takes specialized instrumentation to be able to determine. This is not a naked eye thing. But you can use this for things like the sun and the moon. So that is it for your questions and for your video. Have a wonderful week, guys.